10,
CLS go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
Every civilization, from the first humans who gazed up at the night sky to the modern physicists peering through their telescopes, has asked the same question: how far can we go? So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. It is the question that humbles, terrifies, and inspires. The moon was once unthinkable. Mars was once unreachable. But light, the very thing that carries the sun's warmth to our eyes, has always taunted humanity with its perfect constancy, a cosmic speed limit we cannot break. And yet, we dream. Long before engines thundered and rockets clawed their way into orbit, humans measured distance with their bodies. A journey was the ache in the legs, the blistered feet, the uncertainty of whether the land ahead would offer food or death. The horizon was not just a line, it was a promise and a warning. Go too far, and you might never return. Stay too close, and you might never know what lies beyond. That instinct, to push just a little farther, never left us. It followed us across continents, over oceans, and eventually upward, toward the stars. When we ask how far we can travel through space right now, we are not asking a technical question alone. We are asking a human one. We are asking where the boundary lies between imagination and reality, between desire and physics, between hope and the unforgiving laws of the universe. Because space does not yield to courage. It does not care about ambition. It does not reward bravery. Space only answers to rules, and those rules are ancient. For most of human history, space was not a destination. It was a ceiling. The stars were holes punched into a dome, or fires carried by gods, or souls of the dead watching from above. They were unreachable, not because we lacked technology, but because we lacked the concept of reaching them at all. The earth felt infinite beneath our feet. The sky felt infinite above our heads, and infinity, by its very nature, does not invite travel. It invites worship. But slowly, painfully slowly, humanity learned a dangerous idea. The heavens were not divine glass. They were places. When early astronomers realized that the wandering lights in the sky were worlds, not omens, something irreversible happened. Distance transformed from mystery into challenge, and challenges are invitations. Look up on a clear night, and the stars feel close, close enough to touch, close enough to reach if we could just climb high enough, build tall enough, fly fast enough. That illusion is one of universe's cruelest tricks. Because the night sky compresses unfathomable distances into something the human mind can tolerate, it hides the truth behind beauty. It lets light that has traveled for years, sometimes thousands of years, fall gently onto our retinas as if it had always been waiting for us. When we ask how far we can travel right now, we must first confront this deception. Space is not empty in the way an open field is empty. It is empty in the way an ocean between continents is empty, vast, hostile, and indifferent. And we are not built for it. Not our bones, not our blood, not our instincts. Everything about us evolved for a narrow band of pressure, temperature, gravity, and radiation. Earth is not just our home, it is our shield. Remove that shield, and the universe wastes no time reminding us that we do not belong. The first true step toward answering our question came not with a leap, but with a calculation. Escape velocity. The realization that leaving Earth was not about height, but about speed. That to go up and never fall back down, you had to outrun gravity itself. Not metaphorically, literally. It was a sobering number. Over 11 kilometers per second. Faster than any bullet, faster than any storm, faster than anything humans had ever built. And yet, once it was known, it became inevitable. Because humans do not forgive numbers that tell them no. When the first artificial satellites slipped free of Earth's grip, humanity experienced a quiet, terrifying revelation. The sky was no longer a boundary, it was a road. But roads have costs: fuel, time, mass, risk. Every kilometer gained upward demanded sacrifice downward. Every extra second in space meant less margin for error. The question of how far immediately became a question of how much can we afford to lose. Here is the first uncomfortable truth we must face early. When we talk about how far we can travel, we must decide who we are. Humans or human-made machines? Because the difference is enormous. Machines do not need air. They do not fear radiation. They do not suffer loneliness. They do not require return tickets. A probe can drift for decades in silence and still be considered successful. A human cannot. So the answer to our question splits in two almost immediately. One path belongs to flesh and breath. The other belongs to metal and code. And those paths diverge faster than most people realize. Before we even leave Earth physically, there is a distance we must travel mentally. Imagine standing on a world where help is always minutes away, where food, water, gravity, and protection are defaults, not luxuries. Now imagine leaving that world, knowing that every meter of distance makes rescue less likely, not more. At some point, distance becomes irreversible. The moon, only a few days away, already crosses that line. A malfunction there is not an inconvenience. It is a death sentence delayed by hope and engineering. And yet, humans went. When the Apollo astronauts set foot on the moon, they did something no human had ever done before or since. They traveled farther from Earth than any other human beings in history, not just in distance, but in dependency. Earth was no longer beneath them. It was a pale object in the sky. NASA did not call it courage. They called it acceptable risk. The difference matters. From Earth to the moon is about 384,000 kilometers. A number so large it feels impressive, but in cosmic terms, it is barely a step off the porch. You could fit the Earth and moon inside the sun with room to spare. You could line up every planet between Earth and the moon and still have empty space left over. Distance in space is deceptive. It grows not linearly, but exponentially. Each new destination is not just farther, it is harder in ways that stack mercilessly. Fuel requirements explode. Communication delays stretch conversations into monologues. Supplies multiply. Failure compounds. At some point, distance stops being about travel and becomes about endurance. This brings us to the heart of the question. Not how far could we travel someday? Not how far we dream of going, but how far we can travel right now with the technology we actually possess, the budgets we actually approve, and the human limits we cannot negotiate away. Right now, in this moment of history, humanity exists in a narrow shell around Earth, a fragile halo of satellites, stations, and occasional missions that never stray far from home. Low Earth orbit is crowded with machines. Humans visit it regularly. It is familiar, it is routine. Beyond that, the traffic thins dramatically. Beyond that, it nearly stops. Even when we leave Earth, Earth never truly lets go. Gravity stretches its influence far beyond the atmosphere, pulling at spacecraft, shaping orbits, demanding constant correction. Every journey outward begins with a negotiation. How much fuel to burn now? How much to save for later? How much risk to tolerate? And fuel, unlike ambition, is finite. This is why the question of distance is inseparable from the question of return. A journey outward is meaningless if it strands its traveler forever, unless that is the goal. Right now, human space travel is defined by a single, unbreakable rule. Everyone must come home. That rule, shrinks the universe dramatically. At first glance, asking how far we can travel through space might sound like curiosity for curiosity's sake, a thought experiment, a topic for documentaries and late-night wonder. But buried beneath it is something far more urgent. This question defines the boundaries of human expansion. It tells us whether Earth is a cradle we will one day outgrow, or a shoreline we will never truly leave. It determines whether humanity is a planetary species or a cosmic one. And perhaps most uncomfortably, it forces us to confront the possibility that the universe is not waiting for us, that it does not care whether we arrive or not. Space does not answer our questions with words. It answers with silence, radiation, and distance. It answers by reminding us that the nearest star is not near in any meaningful sense, that even light, the fastest thing in existence, takes years to cross what looks like a single step on the sky. And so, when we ask how far we can go right now, the answer is not a destination. It is a boundary, a line drawn not by desire, but by reality. We will move outward, step by step, following the exact limits of human reach. We will trace how far our bodies can go, how far our machines have gone, and where, precisely, the universe tells us to stop. Not forever, but for now. Because the most important thing about a boundary is not that it exists, it is that one day, someone will try to cross it. Before humanity ever dreamed of crossing the void between stars, it had to confront a quieter, more intimate enemy. Not space, not distance, but home. Because Earth is not just the place where we began. It is the place that refuses to let us go. From the ground, Earth feels gentle, stable, forgiving. Gravity keeps us rooted. Air fills our lungs without effort. Radiation is filtered. Temperatures stay within survivable bounds. The planet cradles us so completely that we rarely notice the price it demands for protection. But the moment we try to leave, Earth reveals its other nature, a warden. Gravity is the most familiar force in our lives, and because of that, the most underestimated. We experience it as weight, as pressure in the feet, as the reason objects fall. It feels passive, constant, harmless. It is anything but. Earth's gravity is a deep well, and humanity lives at the very bottom of it. Every step we take upward, every meter, every kilometer, is borrowed against an invisible debt that must be paid in energy. To leave Earth permanently, a spacecraft must reach escape velocity, the precise speed required to break free from the planet's gravitational grip without falling back. This number is merciless, roughly 11.2 kilometers per second. Not eventually, not on average, but now, continuously, before gravity drags you back down. This is why space travel is not about height. It is about speed. A balloon can rise higher than many early rockets, but it will always fall back. Only velocity grants freedom, and velocity demands sacrifice. When people imagine spacecraft, they picture sleek machines gliding effortlessly into space. The reality is far more brutal. A rocket is not a vehicle in the way a car or airplane is a vehicle. It is a controlled explosion that burns the vast majority of its mass just to lift the remainder a little higher. More than 90% of a typical launch vehicle is fuel. Not because engineers lack creativity, but because physics leaves no room for negotiation. Every kilogram added, food, water, shielding, instruments, requires more fuel. More fuel requires more structure. More structure requires more fuel still. This vicious cycle is known as the rocket equation, and it is one of the most punishing constraints in all of engineering. Earth enforces it relentlessly. This is the first great limiter on how far we can travel right now. We must first pay the full cost of leaving home. Before gravity tightens its grip, Earth sets another trap: air. The atmosphere protects us from meteors, radiation, and the vacuum of space. It also resists anything that tries to punch through it at high speed. Launching a rocket means slamming into layers of air that fight back with heat, pressure, and drag. Engines must burn hotter and harder, just to overcome resistance that exists solely because Earth keeps us alive. And the faster you go, the worse it gets. Friction heats surfaces to thousands of degrees. Structural stress threatens to tear vehicles apart. Tiny miscalculations amplify into catastrophic failures. Earth does not make departure impossible, but it makes it expensive, and danger scales with ambition. There is a strange irony at the edge of space. To an outside observer, a spacecraft in low Earth orbit looks free. It circles the planet every 90 minutes, floating above the atmosphere, bathed in sunlight. Astronauts drift weightless, untethered from the ground. But orbit is not escape. Orbit is falling, forever missing the ground. A spacecraft in orbit is still firmly trapped by Earth's gravity. It is moving sideways fast enough that as it falls, the planet curves away beneath it. One wrong maneuver, one loss of speed, and it will spiral back into the atmosphere and burn. True freedom requires more speed, more fuel, more risk. And that difference, the gap between orbit and escape, is enormous. Right now, almost all human space activity exists on the wrong side of that line. There is another reason Earth's grip is so strong, and it has nothing to do with physics. Distance from Earth equals distance from rescue. Low Earth orbit is close enough that help can arrive. Supplies can be sent. Mistakes can sometimes be corrected. Astronauts know that beneath them, the world is still reachable. Beyond that, comfort evaporates. The moon is 3 days away, too far for emergency response, too far for improvisation to reliably save lives. Mars is months away. Beyond that, help is not delayed, it is irrelevant. Right now, humanity chooses to remain close not because we cannot leave, but because the cost of doing so remains unacceptably high. Earth's invisible cage is reinforced by caution. On Earth, radiation is an abstraction, a medical dose, a warning sign, something regulated and controlled. In space, it is omnipresent. Earth's magnetic field wraps the planet in an invisible cocoon, deflecting charged particles from the sun and deep space. It is one of the most important reasons life exists here at all. The moment we leave that field, we are exposed. Solar radiation damages cells. Cosmic rays punch through tissue, altering DNA. Over time, exposure increases cancer risk, degrades the nervous system, and threatens fertility. Right now, we do not have perfect solutions to this problem. Shielding adds mass. Mass demands fuel. Fuel demands sacrifice elsewhere. Earth's protection is effortless. Space's hostility is not. Distance in space is inseparable from time. A journey is not just measured in kilometers, but in days, months, years spent exposed to everything Earth shields us from. Long-duration missions strain bodies in ways we are still learning to understand. Bones weaken, muscles atrophy, vision changes. The immune system falters. The brain itself may be altered by prolonged weightlessness and radiation. Earth's gravity is not a nuisance, it is a stabilizer. Remove it, and the human body begins to unlearn itself. This is another reason our reach remains short right now. The farther we go, the longer we must endure environments we are not designed for. There is a cruel joke hidden in planetary physics. Earth is one of the hardest places in the solar system to launch from. Its gravity is strong. Its atmosphere is thick. Its escape velocity is high. Smaller worlds, like the Moon or Mars, are far easier to depart once you are already there. But to reach those worlds, you must first escape Earth. This means that nearly all the energy cost of interplanetary travel is paid at the very beginning. Earth collects its toll up front, before you even glimpse the stars. Until that toll becomes cheaper, through radically new propulsion methods or launch systems, human travel will remain tightly constrained. It is tempting to frame Earth as an antagonist, a planet that traps us, a force that holds us back from destiny. But this framing misses something essential. Earth's cage is also a sanctuary. The same gravity that resists our departure keeps our oceans in place. The same atmosphere that fights our rockets gives us breath. The same magnetic field that traps us also shields us. The universe beyond is not waiting to welcome us. It is waiting to kill us, efficiently and without malice. Right now, Earth is the only place where humanity exists effortlessly. Every step away from it increases the cost of survival. That reality defines how far we can travel right now more than any dream ever could. When people imagine the limits of space travel, they picture distant stars, alien worlds, black voids between galaxies. But the first and most powerful boundary is much closer. It begins at sea level. It rises through clouds and jet streams. It thins into blue-black sky. And it ends where gravity finally loosens its grip. Earth's invisible cage is not made of walls. It is made of requirements, energy, precision, endurance, acceptance of risk. Until those requirements change, humanity's reach will remain measured, cautious, and close to home. We will cross the first true milestone beyond this cage, not with machines, but with human bodies. We will trace the farthest distance humans have ever traveled and ask a sobering question. Did we reach our limit, or did we stop just short of it? Every journey has a moment where it stops being theoretical, a point where ideas harden into metal, where equations become fire, where a species places its own fragile body into the unknown and asks the universe a question it cannot take back. For humanity, that moment came not when we first dreamed of the stars, but when we decided to go ourselves, not with machines, not with messages, but with breathing, fearing, hoping human beings. And the distance we reached, how far we physically carried our own lives away from Earth, remains one of the most sobering facts in our entire history. Because it is far less than most people think. Before we talk about the farthest humans have ever traveled, we must talk about how little distance it actually took to change everything. The first human space flights did not race toward the stars. They barely slipped beyond Earth's skin. A few hundred kilometers above the surface, humans crossed an invisible threshold. The sky faded to black. The planet curved beneath them. Gravity loosened its grip just enough to create something no human had ever experienced before. Weightlessness. It was disorienting, liberating, terrifying. Up there, Earth was no longer a ground. It was a view. And for the first time in our species' existence, humans were not standing on a planet. But this was still Earth's neighborhood, a cosmic front porch, close enough to return within hours, close enough that rescue was possible, close enough that mistakes were survivable. This region, low Earth orbit, became humanity's first permanent foothold beyond the atmosphere. And it is where most human space travel still lives today. Orbiting laboratories proved something critical. Humans could survive in space longer than days. Weeks turned into months, months into nearly a year. Bodies adapted, imperfectly, but enough. Bones weakened, muscles shrank, fluids shifted, but life continued. From this narrow shell above the planet, astronauts looked down and saw Earth as a whole. Borders vanished, conflicts shrank, storms moved like living things. Night revealed veins of light where cities breathed. The psychological effect was profound, but in terms of distance, it was almost nothing. Humans were still closer to the ground beneath their feet than to the moon above their heads. The moon forced a decision. It was not just farther. It was separate. Reaching it meant leaving Earth orbit entirely. It meant committing to a trajectory that could not be undone easily. It meant days of travel through empty space with no backup and no margin. When humans went to the moon, they crossed a boundary that still has not been crossed again. The farthest humans have ever traveled from Earth occurred during the Apollo missions, particularly during the voyage that first carried people around the moon and back. At that moment, 3 human beings were farther from home than any others before or since. Earth shrank into a distant sphere, not beneath them, not around them, but behind them. They were not orbiting Earth anymore. They were on their own. One photograph captured the true meaning of that distance. Earth rising over the moon's horizon. Not large, not dominant, but fragile. Blue. Alone. From that distance, Earth was no longer the center of everything. It was a place. One place. A small one. And the realization was crushing. Distance does not just change where you are. It changes who you are. The humans who went that far carried something back that no mission before or after has fully replicated. The understanding of separation. Not metaphorical separation, physical separation. There was no quick return, no orbital safety net, no planet beneath them. If something went wrong, the universe would not negotiate. Landing on the moon was not just an achievement, it was a revelation. It revealed exactly how thin the margin was. Every breath was recycled. Every step was calculated. Every second depended on machines working perfectly in an environment that actively tried to kill them. The moon had no air to soften impacts, no magnetic field to shield radiation, no gravity strong enough to hold an atmosphere, no mercy. And yet, humans walked there. Briefly, carefully. Then they left. And that fact matters. Because despite the triumph, humanity did not build cities on the moon. We did not establish a permanent presence. We did not continue outward from there. We touched the edge of our reach and retreated. The reason is not mystery. It is arithmetic. Distance costs. Every kilogram sent to the moon required staggering amounts of energy. Every mission demanded resources that could not be justified indefinitely without a compelling reason. Politics shifted. Priorities changed. Risk tolerance shrank. The universe did not stop us. We stopped ourselves. And that decision quietly defined the limits of human presence for decades to come. It is worth stating plainly, no human has traveled farther from Earth than those Apollo astronauts. Not since, not before, not even close. Every astronaut who has flown since has remained within Earth's gravitational embrace. Even those living aboard the International Space Station are closer to Earth than travelers on a long-haul flight are to the opposite side of the planet. The moon remains the outermost boundary of human physical presence, a boundary drawn over half a century ago. From Earth to orbit is difficult. From orbit to the moon is vastly harder. From the moon to anywhere else is exponentially worse. This scaling effect is why the moon matters so much in this discussion. It represents a cliff in difficulty. Human bodies require protection, life support, redundancy, escape options. Machines can fail silently. Humans cannot. Every added day of travel multiplies exposure to radiation, isolation, mechanical failure, and psychological stress. Right now, we do not send humans farther, not because we lack imagination, but because we understand the cost too well. Mars looms large in public imagination. It feels close, familiar, almost reachable, but Mars is not the moon. It is months away, not days. Rescue is impossible, communication is delayed, abort options vanish once you commit. A mission to Mars is not exploration, it is exile with the hope of return. And while plans exist, studies accumulate, and optimism persists, the reality remains unchanged. No human has ever gone there. The edge of human presence remains frozen in time, halfway between Earth and nowhere. We like to tell ourselves that human space travel is accelerating, that we are on the brink of becoming an interplanetary species. But measured honestly, by the farthest distance a human body has traveled from Earth, we are not advancing. We are holding. We have learned how to survive longer, not how to go farther. This is not failure, it is restraint. Because space punishes overconfidence faster than any environment we have ever faced. The Apollo missions were not inevitable. They were not guaranteed. They were a narrow convergence of technology, political will, risk tolerance, and human courage. Remove any one of those, and the boundary would never have been crossed. This is why the edge of human presence feels almost mythological today. A relic of a moment when humanity briefly leaned farther into the void than it ever has again. and then stepped back. So when we ask how far humans can travel through space right now, the answer is not speculative. It is historical. It is the moon, 3 days away, 250,000 miles, a distance that took everything we had and demanded we turn around. Beyond that point, human presence fades into silence. Machines continue, signals travel on, but flesh and breath stop there, at least for now. We will stand on that silent surface and look outward, not with human eyes, but with the understanding of what it cost to get there. Because the moon is not just a destination, it is a warning, and it is a promise. There is anywhere beyond the moon, where humanity's presence changes form. No breath fogs a visor, no heartbeat echoes inside a suit. No fear, hope, or wonder is felt by flesh and blood. Beyond that point, we do not go ourselves. We send surrogates, metal bodies, silent instruments, machines that do not feel distance the way we do, and therefore can endure what we cannot. Because when our bodies stopped, our machines kept moving, and they have never stopped since. The decision to send machines instead of humans was not philosophical, it was practical. Machines do not need air. They do not need gravity. They do not suffer radiation sickness. They do not panic when something goes wrong. A machine can drift alone for decades without complaint, powered by dwindling energy, answering questions long after the hands that built it have aged or died. In space, this matters more than bravery ever could. Once humans reached the moon and understood the cost of sending bodies farther, the path forward became clear. If we wanted distance, we would have to give up presence. So we built explorers that could survive where we could not. Early space probes were fragile by modern standards. Limited computing power, narrow mission goals, short lifespans. But they had one advantage humans never would. They could fail without tragedy. Each mission taught us how space behaves when no one is there to intervene, how radiation accumulates, how electronics degrade, how trajectories drift over time. Every failure was a lesson written in silence. Every success extended our reach. Once machines escaped Earth orbit, distance began to grow rapidly. The moon was no longer the outer boundary. Probes slipped past it effortlessly, using gravity not as an enemy but as a tool. Gravity assists turned planets into slingshots. A spacecraft could steal momentum from a world and fling itself outward without burning additional fuel. This trick changed everything. Suddenly, distance was no longer limited by propulsion alone, but by patience. And machines have infinite patience. Robotic explorers visited every major world in the solar system. They photographed storms larger than Earth, skimmed the rings of gas giants, touched alien surfaces, listened to winds that never carried sound. Each encounter pushed the frontier outward, not in kilometers, but in comprehension. And yet, these were still nearby destinations in cosmic terms. The true leap came when we decided not just to visit planets, but to leave the solar system itself. 2 machines carry that distinction: the Voyager probes. Launched in the late 20th century, they were never designed to be eternal travelers. Their primary missions were planetary flybys, brief encounters with giant worlds made possible by a rare alignment of planets. But once those missions ended, something extraordinary happened. They kept going. Powered by long-lived nuclear sources, they drifted outward, slowly, relentlessly, moving farther from Earth every second. No human followed. No human could. Knowing these machines would outlive their usefulness, and perhaps humanity itself, engineers gave them something strange: messages, golden records etched with sounds and images of Earth, music, voices, greetings in dozens of languages. Not because anyone expected them to be found, but because sending them felt necessary. A quiet acknowledgement that these machines were carrying more than data. They were carrying evidence. Proof that once, on a small planet orbiting an ordinary star, something reached outward and wondered if it was alone. There is no sign marking the edge of the solar system, No wall, no gate, no dramatic transition. There is only a gradual thinning of the sun's influence, a region where solar particles give way to interstellar space. When the Voyager probes crossed this boundary, they became the first human-made objects to enter the space between stars. No celebration echoed across the void, but the milestone mattered. Humanity had touched interstellar space, not with hands, but with intention. Unlike human missions, these machines were never meant to come home. There were no return trajectories, no recovery plans, no rescue contingencies. Once launched, they were committed to a one-way journey, measured not in years, but in lifetimes. This is another reason machines can go farther than humans right now. We are unwilling to abandon our own bodies, but we are willing to abandon our creations. That willingness buys distance. Even machines face limits. As distance grows, signals weaken. Data rates slow. Commands take hours, then days, then eventually become pointless. At extreme distances, a spacecraft becomes autonomous by necessity, not because it is intelligent, but because Earth is too far away to help. This creates a strange form of isolation. The machine continues, but the conversation fades. Eventually, it becomes an artifact rather than an explorer. Somewhere in the darkness, far beyond the orbits of planets, human-made objects are drifting silently. They are colder than anything on Earth, more alone than any organism has ever been, moving through regions where stars are distant pinpricks rather than neighbors. They carry no awareness of their achievement, but their existence answers a critical part of our question. Right now, human-made machines have traveled tens of billions of kilometers from Earth. They have left the influence of our star. They have entered the space between stars. They are moving outward still. Given enough time, they will pass near other stars, not as visitors, but as debris. This is the maximum physical reach of humanity at this moment. Not a colony, not a ship, not a crew, a handful of silent messengers. But distance alone is not victory. These machines cannot adapt. They cannot repair themselves indefinitely. They cannot change course meaningfully once power fades. Eventually, they will go dark. And when they do, humanity's physical reach will stop expanding altogether. No new footprints will appear beyond them unless something fundamental changes. The fact that our farthest reach is mechanical is not a failure. It is a reflection of realism. We understand now that the universe is not scaled for us, that bodies evolved on planets do not belong between stars. So we extend ourselves indirectly, through tools, through signals, through artifacts that may outlast memory itself. Machines have taken us farther than humans ever could, for now. But even they face limits imposed by time, power, and physics. We will confront the most unforgiving of those limits, distance itself, not as a number, but as a tyrant that stretches travel into centuries and turns nearby stars into unreachable dreams. Because reaching interstellar space is not the same as reaching another star, and the gap between those two achievements is larger than everything we have crossed so far combined. When human footsteps stopped, silence did not follow. Instead, something quieter took over. No voices, no heartbeats, no fear of death. Only machines, moving steadily outward, carrying humanity farther than flesh ever could. If human spaceflight is a story of courage and restraint, robotic exploration is a story of endurance. Machines do not conquer distance by defying it. They accept it. They move slowly, patiently, sometimes blindly, but relentlessly. This is how humanity has traveled farther than it ever physically could. The universe is not designed for biology. Radiation tears through DNA. Vacuum boils blood. Isolation fractures minds. Time erodes bodies. Machines suffer none of this. They do not care if a journey takes years instead of weeks. They do not need windows, sleep, gravity, or hope. They do not feel the crushing psychological weight of knowing Earth is a fading star behind them. This makes them ideal travelers in a universe where distance is the greatest enemy. So when humanity reached the moon and realized what lay beyond, the path forward quietly shifted. Not outward with humans, but outward through proxies. Every robotic mission is built around a brutal acceptance. There will be no rescue. If something breaks, it breaks forever. This reality forces a different kind of engineering, one obsessed with redundancy, simplicity, and patience. Commands must travel across millions or billions of kilometers. By the time a problem is detected, hours may have passed, sometimes days. Machines must make decisions alone. In a strange way, the farther they go, the more independent they become. Not because they are intelligent, but because Earth is too far away to matter in real time. Distance creates autonomy. Machines mapped worlds humans may never see firsthand. They plunged through the clouds of gas giants. They skimmed ice-covered moons. They photographed landscapes no human eye has ever seen directly. Robotic explorers turned the solar system from points of light into places. Mars became a world of dust storms and dried riverbeds. Jupiter revealed storms older than civilization. Saturn's rings emerged as intricate systems of ice and gravity. Each discovery expanded humanity's mental territory, even as our physical presence remained close to Earth. This is a crucial distinction. Distance is not just about travel, it is about knowledge. And machines gave us knowledge without demanding we pay the ultimate biological price. One of the most important advantages machines have is their ability to exploit gravity mercilessly. Humans require smooth trajectories, safety margins, and abort options. Machines do not. A robotic probe can dive close to a planet, steal its momentum, and fling itself outward at speeds no rocket could achieve alone. These gravity assists allow machines to gain tremendous velocity without carrying extra fuel. This is how relatively small spacecraft reach the outer planets and beyond. Distance, once again, was conquered not by strength, but by understanding. Eventually, even the solar system runs out of places to visit. Planets thin into darkness. Solar light weakens. Temperatures plunge toward absolute zero. For machines designed to keep going, this is not an ending. It is a transition. The sun's influence fades gradually. Its magnetic bubble thins. Solar particles give way to interstellar radiation. There is no dramatic border crossing, only a slow realization that home no longer matters. When machines pass this point, they leave behind not just Earth, but the entire system that gave birth to them. They become interstellar travelers. Right now, the most distant human-made objects are moving through interstellar space. They are farther from Earth than any signal sent intentionally, farther than any human body has ever gone, farther than any hope of retrieval. These machines are the physical edge of humanity, not explorers in the romantic sense, not colonists, not pioneers. They are artifacts, evidence that something once reached outward and did not stop. Their journey will continue long after their power fades, long after communication ends, long after anyone remembers the moment they were launched. Distance for them is infinite. As machines travel farther, something subtle happens. They become quieter. Signals weaken with distance, spreading out, dissolving into cosmic noise. Data rates drop from images to numbers, from numbers to single bits. Eventually, communication becomes symbolic. A whisper sent into darkness, hoping something, anything, hears it. At extreme distances, commands are pointless. By the time instructions arrive, conditions have changed, or the machine has already failed. At that point, the traveler is truly alone. This is the final cost of distance. Despite their reach, machines have limits humans do not. They cannot adapt creatively. They cannot repair themselves indefinitely. They cannot build infrastructure. They cannot decide new goals once their mission ends. They are perfect for exploration, but terrible for permanence. A probe can tell us what a world is like. It cannot live there. It cannot grow there. It cannot make that place matter beyond data. So while machines extend our reach, they do not expand our presence. That distinction will haunt every future attempt to go farther. From Earth, it is tempting to believe that machines make distance irrelevant, They do not. They simply make it survivable. Even the farthest probes move at speeds that make interstellar travel absurdly slow. Years become decades. Decades become centuries. Centuries become millennia. Reaching another star is not impossible for machines, but it is meaningless within human timescales. Distance still wins. Robotic exploration has revealed something profound. The universe is not waiting to be explored quickly. It is waiting to be explored slowly or not at all. Every planet, every moon, every empty region between stars is separated not just by space, but by time. And time is the one resource no technology has truly conquered. Machines accept this reality. Humans resist it. That is why machines go farther. As you read this, human-made objects are moving farther from Earth than ever before. No headlines announce their progress. No celebrations mark their milestones. No one feels the moment when another 1,000,000 kilometers slip behind them. Distance accumulates quietly, and with each passing second, humanity's physical reach grows, imperceptibly, irrevocably, without a single human body involved. This is the paradox of our era. We are expanding without moving, yet even machines face a wall. Power fades, instruments degrade, cosmic radiation corrupts memory, time erodes everything. Eventually, all travelers fall silent. And when they do, humanity's reach freezes again, locked at whatever distance those machines achieved. Unless something changes, unless propulsion improves, unless power becomes abundant, unless distance itself is redefined. Machines have taken us farther than humans ever could so far. But they have also revealed the true villain of space travel. Not gravity, not radiation, not engineering, distance itself. We will confront that enemy directly. We will strip away romance and ambition and look at distance as it truly is. Not a challenge to overcome, but a force that stretches travel into lifetimes and turns nearby stars into unreachable mirages. Because until we understand distance, we do not understand how far we can truly go. There is a world that has haunted human imagination longer than rockets, longer than telescopes, longer even than science. A red point in the sky, a wandering ember that never stays still, a place that looks from Earth almost familiar. That world is Mars. And when people ask how far we can travel through space right now, they almost always mean one thing. Can we go there? Mars feels like the next logical step. Not a star, not an impossible fantasy. A planet, a destination with ground, gravity, days, seasons. Close enough to imagine walking on. Far enough to remind us that imagination is cheap. Mars tricks us with perspective. At its closest, it is only tens of millions of kilometers away. On cosmic scales, that feels trivial. On paper, the number looks manageable. The planet even shows detail through amateur telescopes, polar caps, dark regions, dust storms. It feels reachable. But space is cruel to intuition, because distance in space is not fixed. It stretches and shrinks as planets move, turning the gap between Earth and Mars into a constantly changing chasm. Sometimes the journey is long, sometimes it is longer, and unlike the Moon, Mars is never a short trip. Even under ideal conditions, it is a voyage measured in months, not days, not weeks, months. That alone changes everything. The Moon taught us how to survive away from Earth briefly. Mars demands that we survive away from Earth continuously. During a Mars transit, astronauts would live inside a small enclosed spacecraft for half a year or more. No resupply, no rescue, no turning back once committed. Every breath recycled, every drop of water reused, every system relied upon without backup from home. Time becomes the dominant threat. Not because of boredom, but because exposure accumulates. Between Earth and Mars, there is no planetary shield, no magnetic cocoon, no thick atmosphere, no mercy. Astronauts traveling to Mars would be exposed to constant radiation from the sun and from deep space. Unlike short missions, this exposure stacks relentlessly over time. Radiation does not kill dramatically. It degrades quietly. DNA damage increases cancer risk. Neural tissue suffers subtle harm. The body ages faster than it should. Right now, we do not fully understand the long-term effects of this exposure on human beings. And what we do understand is not comforting. Mars has gravity, but not enough. About a third of Earth's gravity, it is strong enough to pull you down, but too weak to keep your body fully healthy. Bones weaken, muscles shrink, cardiovascular systems adapt poorly. This creates a paradox. The journey to Mars weakens astronauts. Mars itself cannot fully restore them, and the return journey would happen with bodies already compromised. The planet does not save you from space. It only changes the way space harms you. On the Moon, communication delays were seconds. On Mars, they stretch into minutes. A conversation becomes a series of messages sent into the future and answered from the past. Real-time help is impossible. Emergencies must be handled alone. If something breaks, Earth cannot guide hands in the moment. Instructions arrive too late. Mars missions require not just technical skill, but psychological resilience beyond anything previously demanded. You are not just far from home, you are temporarily isolated from it. One of the most unsettling realities of Mars travel is this. Once you leave Earth, there is no safe way to turn around. Orbital mechanics do not allow casual reversals. Fuel budgets are tight. Trajectories are commitments. A Mars mission is not a round trip in the traditional sense. It is a long, irreversible arc through space that only returns to Earth because it was designed that way from the beginning. If something goes catastrophically wrong, there is no rescue mission. There is only endurance or silence. Reaching Mars orbit is only half the battle. Landing is harder. The atmosphere is too thin to slow spacecraft easily, but thick enough to cause intense heating. Parachutes struggle. Retro rockets must fire precisely. Mars has claimed more robotic missions than it has welcomed. For humans, failure would not be a data loss. It would be final. Let us assume everything works. The spacecraft arrives. The landing succeeds. The crew steps onto Martian soil. They have not arrived at safety. Mars is cold, dry, irradiated, hostile. There is no breathable air, no liquid water at the surface, no protection from solar storms. Living on Mars means living inside machines, habitats, suits, systems that must function perfectly for years. Mars is not a new Earth. It is a temporary shelter inside an enemy environment. Perhaps the least understood challenge of Mars is isolation. Not the isolation of solitude, but the isolation of irrelevance. From Mars, Earth is a bright star, a memory, a place you cannot return to quickly, no matter how badly you want to. Families age, societies change, events unfold without you. You are not just far away, you are removed. This psychological distance may be more dangerous than radiation or engineering failure. Humans evolved to live within communities, not across planetary gaps. Mars is not unreachable. We can design spacecraft. We can plan trajectories. We can simulate habitats. But right now, the risks outweigh the rewards. The cost is enormous. The danger is unacceptably high. The margin for error is nearly zero. Unlike the Moon, Mars offers no quick victories, no brief visits, no easy retreat. It demands commitment on a scale humanity has not yet agreed to make. Mars forces us to confront an uncomfortable truth. We are not limited by technology alone. We are limited by biology, psychology, ethics, and willingness to accept loss. A Mars mission would likely succeed only if humanity accepts the possibility, perhaps the probability, that people will die doing it. Right now, that price is too high. In terms of distance, Mars is not far compared to the stars, but in terms of consequence, it is farther than anything humans have ever attempted. It lies beyond easy rescue, beyond fast communication, beyond return as an option. Mars is the threshold where space travel stops being exploration and becomes existence under constant threat. That is why it remains unvisited by humans. Not because we cannot go, but because we understand what going truly means. Mars represents the boundary between nearby space and deep commitment. Crossing it would redefine humanity's relationship with the universe. It would prove that we are willing to live, not just visit, beyond Earth. But until that day comes, Mars remains a symbol rather than a destination. A reminder that distance is not just measured in kilometers, but in sacrifice. So when we ask how far we can travel through space right now, Mars stands as a paradox. Close enough to dream about every night, far enough to demand more than we are ready to give. It is the nearest place where our limitations stop being technical and start being existential. We will move beyond Mars, not to another world, but into the cold arithmetic that governs all space travel. We will confront the true tyrant of the universe, distance itself, and why even reaching nearby stars remains a fantasy measured not in decades, but in lifetimes. After we leave Mars behind, after we acknowledge that humans cannot travel safely to even our nearest planetary neighbor without months of isolation and risk, we encounter the true limit to space travel, distance itself. Distance is not a number on a page. It is not a measurement that can be conquered by more fuel, bigger rockets, or longer missions. Distance is a force, a silent, omnipresent tyrant that stretches time, amplifies danger, and renders even the nearest stars effectively unreachable with current technology. Until we understand the tyranny of distance, we cannot understand how far we can truly go. Our solar system is vast, but it is a local neighborhood. The nearest star to Earth, Proxima Centauri, lies roughly 424 light-years away. That is about 40 trillion kilometers. 40 trillion. To put that in perspective, the Moon is roughly 384,000 kilometers from Earth. Mars, at its closest, is around 55 million kilometers. The distances escalate dramatically beyond our planetary backyard. A journey to the nearest star using conventional rockets would take tens of thousands of years. Even the fastest probes humans have ever built, such as Voyager 1, moving at 17 kilometers per second, would take over 70,000 years to reach Proxima Centauri. Distance is no longer something to overcome. It is a scale of time. Even light, the fastest entity in the universe, takes time to traverse these gaps. A beam from Proxima Centauri requires 4.24 years to reach Earth. Messages from hypothetical starships would be delayed by years, decades, or centuries. Communication becomes asynchronous to the extreme. For human travelers, this is fatal. Decisions made in isolation cannot rely on Earth's intervention. The further the distance, the more autonomous survival must be. In other words, distance transforms travel into self-contained existence. We are biologically unprepared for such scales. The tyranny of distance is also economic. The energy required to reach interstellar destinations with conventional propulsion is staggering. To accelerate a spacecraft to even 10% the speed of light, a theoretical target for near-future interstellar travel, requires energy equivalent to a small nuclear reactor running at full capacity for years, just for a single kilogram of mass. Multiply that by a crewed ship with life support, supplies, and shielding, and the numbers become almost absurd. Every gram sent farther multiplies the fuel cost exponentially. This is why current technology restricts us to robotic proxies for anything beyond our solar system. Relativity offers a theoretical escape from tyranny. Near-light speeds can compress subjective time for travelers, allowing them to reach distant stars in what feels like months or years. But this comes at a cost. The energy requirements for such speeds are astronomical. Even approaching a fraction of the speed of light requires propulsion far beyond current engineering. Furthermore, time dilation creates paradoxes. Travelers may experience a few years, but decades or centuries could pass on Earth. Humanity on the home planet ages differently than the Voyagers. Home may change beyond recognition. Distance, in this sense, is not only spatial, it is temporal, fracturing human continuity. Even if propulsion and shielding were solved, distance remains biological. Humans are adapted to a single planet in a gravitational field of a particular strength, shielded from cosmic radiation, and living on a planet with a stable environment. Long-term space travel requires coping with microgravity, radiation, psychological isolation, and finite resources. For interstellar missions lasting decades or centuries, human life must be preserved across multiple generations or via suspended animation, technologies that remain speculative. Distance, in this sense, forces a confrontation with our biological limits. Our nearest stellar neighbors, like Alpha Centauri and Barnard's star, may feel close in astronomy books, but for current human capability, they are practically unreachable. Even our most ambitious interstellar probes, theoretical in design, would take millennia to arrive. Humans cannot survive that time frame. Distance converts possibility into abstraction. Our physical reach ends where time, biology, and energy intersect. Stars are no longer destinations, they are points of observation. Distance also isolates consciousness. Messages across interstellar distances travel at the speed of light, so even a two-way conversation would require years. Real-time guidance, instruction, or rescue is impossible. A crew on an interstellar voyage would be completely autonomous. Every problem must be solved with onboard knowledge and skill. Errors may be irreversible. Emergencies cannot be mitigated by Earth. Distance transforms autonomy from a convenience into a necessity for survival. Interstellar travel eliminates logistics. Fuel, food, oxygen, water, medical supplies, all must be carried from the start or produced on board. A single miscalculation can be fatal. Resupply missions are impossible. Earth is no longer a base. It becomes an unreachable memory. Distance forces self-reliance to the extreme, turning every journey into a permanent risk assessment. Distance is also a mental challenge. Humans are social creatures. We evolved in groups with shared goals, communication, and physical proximity. In interstellar travel, humans face extreme isolation. They may never see another human outside their ship. They may lose touch with Earth culturally and temporally. The home they knew may vanish in centuries while they travel. Distance becomes not just a physical barrier, but a psychological one, demanding resilience humanity has never been tested against. All previous sections have addressed near-term travel, Earth orbit, moon missions, Mars expeditions, robotic probes. Interstellar travel shows a different scale. Even the most optimistic near-future technology cannot significantly reduce travel times to the stars without energy sources or propulsion methods far beyond today's capabilities. The tyranny of distance ensures that, for now, humans remain confined to the solar system. Our machines can go farther, but even they move slowly, patiently, inexorably constrained by the same cosmic scales. Distance acts as a filter. It separates ambition from reality. It turns dreams into plans, and plans into experiments. It is indifferent to courage. It does not negotiate with vision. It simply exists, scaling obstacles, amplifying costs, stretching time, and limiting feasibility. The further we attempt to go, the more it dominates every aspect of our planning. For human travel, low Earth orbit is achievable. The moon has been reached. Mars is theoretically reachable but remains risky. Beyond Mars, distance multiplies hazards, resource demands, and time exponentially. For robotic travel, the outer planets can be visited and mapped. Voyager-class probes can drift into interstellar space. Stars remain beyond practical reach. Distance becomes the defining limit of human expansion. Distance forces a reckoning with our place in the cosmos. For all our technology, courage, and ingenuity, we remain localized. The universe is vast. Stars are distant suns. Planets may be habitable, but current human reach is limited to our home system and the machines we send beyond it. Distance imposes perspective. It reminds us of humility. It defines the frontier of our experience. Understanding distance is essential for any future ambition. Interstellar colonization remains speculative. Energy requirements scale beyond imagination. Biological limits constrain human survival. Communication and autonomy become absolute necessities. Until these challenges are addressed, humans cannot travel far beyond Mars. Distance, not imagination, is the ruler. Distance is the ultimate arbiter of space travel. It is more relentless than gravity, radiation, or engineering. It measures ambition against patience, biology, and physics. It tells us where we can go, where machines can go, and where dreams outpace reality. Right now, distance confines humans to the solar system. It confines them to machines that carry our presence silently outward. It defines the limits of exploration, survival, and expansion. To truly transcend it, humanity will need not only technology, but a fundamental redefinition of endurance, life, and time itself. After confronting the unyielding reality of distance, we are left with a critical question. How far could humans travel if we were willing to challenge the limits of physics, engineering, and biology? For now, distance dominates. Mars is the edge of practical human travel. The Moon is our farthest achieved boundary. Robotic probes drift slowly into interstellar space. Beyond that, even light years feel insurmountable. But humanity is nothing if not curious, inventive, and audacious. Across decades of research, some ideas have emerged. Technologies that, if realized, could allow us to push the frontier farther than ever before. This section examines the most promising, the most speculative, and the most audacious concepts humanity has conceived to challenge the tyranny of distance. Rocket fuel, the chemical kind used for Saturn V or Falcon Heavy, is limited. Conventional propulsion cannot accelerate a crewed spacecraft to the speeds necessary for interstellar travel within human lifetimes. Nuclear thermal propulsion, NTP, changes this equation. By heating hydrogen fuel with a nuclear reactor, NTP can produce much higher exhaust velocities than chemical rockets. A crewed mission to Mars using NTP could cut travel time dramatically, reducing exposure to radiation and microgravity hazards. Nuclear electric propulsion, NEP, goes even further. It converts nuclear energy into electricity to power ion engines, which eject particles at extremely high velocities. NEPI is slower to accelerate, but extremely efficient, allowing continuous thrust over long periods, a critical factor for deep space missions. Together, these technologies represent near-future possibilities for pushing human presence beyond low Earth orbit, toward Mars, and potentially into the outer solar system faster than ever before. Imagine a spacecraft so thin and light, it can be pushed by the pressure of light itself. Photons emitted by the sun or powerful lasers. This is the concept behind light sails. Light sails could, in theory, accelerate to a significant fraction of the speed of light without carrying fuel. Projects like Breakthrough Starshot envision sending tiny probes to the nearest stars, propelled by Earth-based lasers. For humans, the challenge is enormous. Carrying life support systems, shielding, and supplies increases mass by orders of magnitude. Nevertheless, light sails illustrate a critical principle. Distance may be overcome not by brute force, but by exploiting subtle, persistent, natural forces. Chemical rockets burn fuel. Nuclear rockets release energy stored in atoms. Fusion propulsion, harnessing the energy of fusing hydrogen nuclei, offers far greater energy density. Fusion-powered spacecraft could accelerate continuously for months or years, approaching speeds that make interstellar travel conceivable. A fusion-powered crewed ship to Mars or the outer planets could reduce transit times drastically. However, controlled fusion remains an unsolved problem on Earth, let alone in a compact, reliable propulsion system for space. Achieving this would represent a revolutionary step, giving humans the ability to extend our reach well beyond the solar system. Antimatter is the ultimate energy source. Matter and antimatter annihilate completely, releasing tremendous energy. A spacecraft powered by antimatter could, theoretically, accelerate close to the speed of light. In practice, antimatter is extraordinarily difficult and expensive to produce. Storage is volatile. A single containment failure would be catastrophic. Despite these obstacles, antimatter propulsion remains a tantalizing theoretical pathway for extreme interstellar travel. If realized, it could transform centuries-long journeys into decades, bringing stars within reach in a human lifetime. Even if propulsion is solved, human biology remains a barrier. Long journeys expose astronauts to radiation, isolation, and limited resources. One proposed solution is cryogenic sleep or suspended animation. By slowing metabolic processes, humans could survive decades or centuries without aging or consuming supplies at normal rates. Cryogenic sleep is currently speculative. Challenges include maintaining organ viability, preventing radiation damage, and managing psychological effects upon revival. However, its successful implementation could allow humans to travel far beyond Mars while minimizing physical and mental strain. Traveling far is one challenge. Surviving there is another. Technologies that allow humans to live off the land are critical for long-term presence. In situ resource utilization, ISRU, harvesting water, oxygen, and fuel from planetary surfaces reduces the need to carry everything from Earth. Terraforming, transforming an alien environment into one capable of supporting human life. Though largely speculative, even partial atmospheric modification could extend human range and reduce dependency on habitats. Distance is not just about propulsion. It is about making alien worlds hospitable enough to survive once we arrive. Extended periods in microgravity have severe effects: muscle atrophy, bone loss, cardiovascular decline. Artificial gravity, created by spinning spacecraft, could mitigate these issues. By designing ships with rotating sections, centrifugal force simulates gravity, preserving human health on multi-year journeys. While feasible in principle, engineering rotating habitats introduces complexity, mass penalties, and new mechanical challenges. Still, it is essential for any serious attempt to travel to Mars or beyond in a biologically sustainable way. Distance exposes humans to cosmic radiation, solar flares, and interstellar particles. Traditional shielding is heavy, reducing spacecraft efficiency. Innovative solutions include magnetic shielding, creating magnetic fields around the spacecraft to deflect charged particles. Water shielding, using water tanks strategically around crew areas to absorb radiation. Regolith shielding, covering habitats with planetary material when on a surface. Radiation management is not optional. It is a survival requirement. Without it, longer journeys are lethal. Distance requires autonomy. Even in the best-case scenarios, humans cannot rely on Earth for guidance in real time. Artificial intelligence and autonomous systems can monitor ship systems, make critical decisions, and maintain life support without intervention. They can also navigate, conduct repairs, and adjust trajectories mid-flight. Future spacecraft may become semi-independent entities, capable of operating far from human oversight, enabling longer, safer voyages. No single technology is sufficient to overcome the tyranny of distance. Instead, progress requires integration, propulsion systems for speed, life support for sustainability, radiation shielding and artificial gravity for health, autonomy for operational independence, sleep technologies for time management. Distance is not defeated by any single breakthrough. It is challenged incrementally by layering solutions. Even with all theoretical technologies, humans remain the limiting factor. Psychology, adaptability, social cohesion, and decision-making under extreme isolation define what is feasible. Traveling to Mars may be within technical reach soon, but interstellar travel tests the very limits of human nature. Distance challenges endurance, courage, patience, and cooperation. In the next few decades, Mars missions may be feasible with NTP, NEP, and ISRU. Robotic probes may explore the outer planets in detail. Light sail experiments may reach nearby stars with small payloads. These achievements will expand human understanding, but will not overcome distance for crewed interstellar travel. They are first steps toward confronting the tyranny directly. Farther, we enter the realm of speculation. Antimatter propulsion or controlled fusion could make interstellar travel practical. Generational ships could allow humans to live and die en route, with descendants arriving centuries later. Warp drives, if possible, would rewrite the rules entirely. For now, these remain theoretical, but they illuminate what is required to move humanity beyond its local neighborhood. Technological ambition reminds us, distance is not immutable, it is negotiable. But negotiation requires ingenuity, patience, and a willingness to confront consequences across decades, centuries, or millennia. Emerging technologies teach us that, while humanity is limited today, the tools to extend our reach may exist. It is not certainty, it is possibility. This reveals a paradox. Distance remains dominant, but humans are not powerless. Every advance, nuclear propulsion, light sails, fusion, AI, cryogenic sleep, represents a potential chisel against the unyielding wall of space. Yet for all the promise, distance still dictates terms. We may move faster, survive longer, and reach farther, but distance will always demand trade-offs, impose costs, and test the limits of our courage, biology, and ingenuity. We will examine what the future holds if we choose to accept those trade-offs, exploring the prospects, timelines, and human ambition necessary to truly transcend our solar system. Having confronted the tyranny of distance and explored the emerging technologies that could challenge it, we now reach the speculative frontier, the possibility of humans traveling beyond the solar system. This section is not about the Moon or Mars, nor about robotic proxies drifting into interstellar space. This is about humans themselves, leaving the cradle of our sun to journey toward other stars. It is the ultimate question of human space travel. How far can we go if we are willing to accept the costs, the risks, and the decades or centuries that may lie ahead? With current chemical propulsion, interstellar human travel is impossible. Even the closest star, Proxima Centauri, is over 4 light-years away, about 40 trillion kilometers. Consider the fastest crewed spacecraft ever launched, the New Horizons probe, traveling at roughly 16 kilometers per second. At that speed, a journey to Proxima Centauri would take over 80,000 years. That is a human lifetime multiplied dozens of times. Even advanced nuclear thermal propulsion, or nuclear electric propulsion, reduces travel time only modestly. While months to Mars is feasible, decades or centuries to other stars remains beyond practical reach. Distance is no longer just a hazard, it becomes the scale of human generational survival. Given the impossibility of reaching nearby stars in a single human lifetime with foreseeable technology, one proposal is the Generation Ship. A Generation Ship is a self-contained spacecraft designed for multi-generational crews. People are born, live, reproduce, and die during the voyage, with the descendants eventually reaching the destination. This concept addresses the time problem but introduces enormous challenges. Life support, air, water, and food must be continuously recycled for centuries. Failures cannot be corrected easily. Genetics. Maintaining genetic diversity over generations in isolation is critical. Psychology and culture. Social cohesion must persist over decades, even centuries. Education, purpose, and mental health must be managed for people born en route. The Generation Ship concept is theoretically possible, but it requires engineering, social, and biological mastery on a scale humanity has never achieved. Another approach to interstellar travel is to place travelers in suspended animation or cryogenic sleep, reducing metabolic activity and the need for life support. This approach has several advantages: reduces food, water, and air requirements, minimizes psychological stress from long voyages, allows a smaller crew to reach distant stars within a single lifetime. However, suspended animation remains largely speculative. The technical hurdles, avoiding cellular damage, restarting life functions safely, and ensuring long-term health, are immense. Even partial success could revolutionize deep space travel, but it is far from reality today. To travel between stars in a human-relevant time frame, we need propulsion far beyond chemical rockets. Some theoretical concepts include Fusion propulsion. Harnessing nuclear fusion for continuous high-speed thrust could reduce travel times to decades instead of centuries. Antimatter propulsion. Utilizing matter-antimatter annihilation to release immense energy. A single gram could provide the energy of thousands of tons of chemical fuel. Light sails. Extremely lightweight ships accelerated by lasers or solar photons, potentially capable of near-light speed travel, though current technology limits crewed missions. These approaches are speculative, but show that interstellar travel is not fundamentally prohibited by physics, only by current engineering and resources. Traveling beyond the solar system exposes humans to cosmic radiation and interstellar particles at speeds approaching a significant fraction of light. Even at slower speeds, prolonged exposure outside Earth's magnetic shield is dangerous. High-energy particles damage DNA, accelerate aging, and increase cancer risk. Shielding becomes a significant mass problem. Heavy materials protect well, but increase propulsion requirements. Lighter solutions may fail to provide sufficient protection. Distance amplifies these risks. Every additional year in transit increases accumulated radiation dose. Distance is not only physical, it is also psychological. Isolation. Crew members may never see Earth again. Communication delays. Even signals traveling at light speed will take years to reach Earth. Guidance, support, and reassurance are impossible. Generational separation. Descendants born en route may never know their origin world. Mental resilience becomes as critical as technical engineering. A ship is not only a spacecraft, it is a society in microcosm. Interstellar missions demand extreme autonomy. Earth cannot monitor every system or intervene in emergencies. Artificial intelligence would act as co-pilot, medic, engineer, and manager, capable of detecting system failures, performing repairs, adjusting trajectories, mediating disputes among crew. Advanced AI is essential to extend human survival across decades or centuries in space, particularly when distance makes Earth irrelevant in real-time decisions. Currently, the nearest stars are the only realistic targets. Proxima Centauri, 4.24 light-years, hosts Proxima b, a planet in the habitable zone. Alpha Centauri A and B, 4.37 light-years, potential exoplanets not yet confirmed. Barnard's Star, circa 6 light-years, with candidate exoplanets. Even these closest stars are extraordinarily far. Reaching them with current human-scale technology is impossible within a lifetime. Consider a spacecraft moving at 10% the speed of light. Journey to Proxima Centauri, chance 42 years. Journey to Alpha Centauri, 44 years. At 1% the speed of light. Journey to Proxima Centauri, 424 years. Traveling at conventional speeds, interstellar travel extends beyond lifetimes, forcing humanity to think in centuries and millennia. Distance thus becomes a scale that exceeds human perception. Interstellar missions require enormous energy. Consider a 100-ton crewed ship accelerating to 10% light speed. Kinetic energy required, trillions of joules, far beyond current power generation. Fuel mass. Chemical rockets are infeasible. Nuclear or antimatter solutions are required. Life support. Continuous recycling of air, water, and food for decades or centuries. Distance transforms from a numerical barrier into a resource constraint on an almost unimaginable scale. Sending humans into interstellar space raises ethical questions. Is it justifiable to commit generations to a journey they did not choose? How do we handle limited genetic diversity in generation ships? Who decides the mission's goals, rules, and governance? Distance makes oversight impossible. The consequences of decisions are amplified across space and time. Before humans attempt interstellar travel, robotic explorers are essential. Surveying exoplanets, testing propulsion technologies, mapping hazards like interstellar dust and radiation. Machines can reach stars centuries ahead of humans, gathering knowledge and preparing the path. Distance ensures that humans will always follow, at least initially, behind these robotic pathfinders. Right now, humans cannot travel beyond the solar system. Distance is too vast. Travel times exceed lifespans. Radiation, isolation, and life support pose unsolved challenges. However, physics does not forbid interstellar travel. It requires advanced propulsion, life support for decades or centuries, autonomous systems and AI, ethical frameworks for multi-generational crews. Interstellar travel is a human dream constrained by distance, resources, and biology, but not by imagination. This leaves us with clarity. Humanity's physical reach is currently confined to the solar system, but potential exists for expansion if we accept multi-generational voyages or cryogenic sleep. We develop propulsion far beyond chemical rockets. We manage life support, radiation, and mental health on unprecedented timescales. Distance is still the ultimate tyrant, but emerging technologies, preparation, and vision provide the blueprint for a future where humans may finally leave the sun's neighborhood behind. We will explore what the first steps toward interstellar colonization could look like, examining Mars as the stepping stone, robotic scouts as pathfinders, and the social and technological milestones required before humans can truly venture between stars. If humanity is to ever escape the confines of the solar system, the journey must begin closer to home. Mars, the red planet, represents not just the next target of exploration, but the gateway to the stars. Understanding how humans might establish a sustained presence there illuminates both our capabilities and limitations for interstellar travel. This section examines the practical, technological, and social steps required to turn Mars from a distant dream into the first outpost of human expansion into the cosmos. Mars occupies a unique position in the hierarchy of potential human habitats, close enough for robotic reconnaissance and potential crewed missions, far enough to challenge human endurance and test life support systems. Its surface, gravity, Arup 38G, and resources offer a practical environment to learn to live off-world. Mars is neither easy nor safe. It is not Earth. It is hostile, cold, irradiated, and resource-limited. Yet precisely because it is challenging, it serves as an ideal proving ground. Before humans can step foot on Mars, machines must pave the way. Rovers like Perseverance and Curiosity gather geological, chemical, and environmental data. Orbiters map surface hazards, track dust storms, and assess potential landing sites. In situ resource utilization, ISRU, experiments test extraction of water, oxygen, and fuel from Martian regolith. These robotic scouts provide the intelligence necessary to reduce human risk. Distance may be small in astronomical terms, but every unknown is amplified by time and isolation when sending humans to Mars. Human arrival on Mars will mark the first time humanity lives off-world. Travel time, 6 to 9 months depending on orbital alignment and propulsion. Life support, closed-loop systems recycling water, air, and waste. Radiation protection, shielding using habitat design, regolith coverage, and possibly magnetic fields. Psychological resilience, teams isolated from Earth for months, relying on onboard autonomy. Even the first missions will stress test every assumption about human survival in deep space, providing critical lessons for future interstellar efforts. Sustained human presence requires self-sufficient habitats, pressurized modules, shielded against radiation and vacuum. Artificial gravity or countermeasures, combating muscle atrophy and bone loss. ISRU integration, producing oxygen from carbon dioxide, extracting water, and potentially generating fuel. Energy systems, solar arrays, nuclear reactors, or hybrid solutions to power habitats and mobility. Living on Mars is not comfort. It is survival under constant scrutiny of engineering and environmental constraints. While immediate survival is the first priority, long-term human expansion might consider terraforming or altering Mars to support life more comfortably, thickening the atmosphere to increase surface pressure and temperature. introducing greenhouse gases to trap heat, generating magnetic fields to reduce radiation exposure. Terraforming remains speculative, but small-scale modifications, greenhouses, pressurized domes, and resource recycling are achievable first steps. These efforts teach lessons about planetary engineering, resource management, and sustaining life far from Earth. Beyond survival, a functional Martian settlement requires an economy. Resource extraction, water ice, minerals, and CO2 for fuel and life support. Manufacturing, using local materials to build tools, shelters, and infrastructure. Energy production, solar, nuclear, or hybrid systems to power habitats and industry. Knowledge economy, robotics, AI, and science missions to create value and feedback for Earth-based research. Sustaining a settlement requires more than life support. It requires activity, productivity, and the ability to adapt to an unpredictable environment. Distance from Earth makes autonomy a necessity. Decisions must be made locally. Governance structures must maintain order, manage resources, and resolve disputes. Ethical frameworks are needed to balance individual rights, group survival, and mission priorities. Mars may serve as a laboratory for governance in isolation, providing insights for eventual interstellar societies. Psychology is as critical as engineering. Isolation, confinement, and distance from Earth stress individuals and groups. Social cohesion, mental health, and leadership are vital for survival. Multi-generational planning. If Mars is to become a stepping stone to interstellar travel, settlers must think in decades, not months. The social dimension of Mars colonization provides a microcosm of challenges humanity would face on any long-duration interstellar voyage. Autonomous systems are essential to reduce risk and extend human reach. AI-assisted habitat management monitors life support systems. Robots perform dangerous tasks, drilling, mining, construction. Communication delays with Earth require independent problem-solving. Mars demonstrates how humans and machines can cooperate over distance, a model for interstellar exploration where autonomy is mandatory. Mars may serve as a launching point for interplanetary and interstellar missions. ISRU could produce rocket fuel from Martian resources, reducing reliance on Earth. Refueling stations in orbit or on Mars enable spacecraft to depart with heavier payloads or higher velocities. Mars could act as a logistical hub, bridging the gap between Earth and the outer solar system. Distance makes Mars a strategic stepping stone. Lessons learned there reduce the cost, risk, and isolation of further travel. Long-term presence requires cultural and educational sustainability. Knowledge must be transmitted between generations, especially if travel and isolation span decades. Art, literature, and recreation are not luxuries. They are vital for psychological resilience. Cultural evolution on Mars may diverge from Earth, a small-scale experiment in human adaptation to distance. Mars is a laboratory not just for science, but for humanity itself. Success on Mars is not measured solely in survival. How long can humans endure? How much infrastructure can be built? How well can humans utilize local resources? Can a small society remain stable and autonomous? These metrics define readiness for longer, riskier journeys beyond the solar system. In many ways, Mars is the ultimate testbed for interstellar ambitions. Distance is significant, though manageable. Risks are high, but not catastrophic on human timescales. Lessons learned inform propulsion, life support, psychology, and governance. Every success or failure on Mars reduces the unknowns for eventual interstellar travel. Mars is not a solution for humanity's desire to spread among the stars. It is still isolated. Resupply from Earth takes months. Survival depends on technology that can fail. Habitats are fragile, and humans are still vulnerable to radiation, disease, and accidents. Mars is a prelude, not a destination. It is a controlled rehearsal for the far more difficult challenge of leaving the solar system entirely. Mars embodies both hope and humility. It is close enough to challenge our ingenuity and far enough to teach lessons about distance, autonomy, and survival. It is the first rung on a ladder that, if climbed successfully, could eventually reach the stars. By learning to live on Mars through robotics, life support, resource utilization, governance, and culture, humanity can test what is necessary to push farther into the cosmos. The next section will examine the technological, social, and psychological preparations required to transform Mars into a true launch pad for interstellar ambition, bridging the gap between local exploration and the vast distances of the galaxy. If Mars is humanity's first step beyond Earth, then it must also become the springboard for ventures beyond the solar system. Section 11 explores how the Red Planet could serve as a launchpad for interstellar exploration, combining technological innovation, strategic planning, and human adaptability into a coherent strategy that makes the stars conceivable, even if still distant. Mars occupies a unique position in the solar system. Lower gravity than Earth, 0.38 g, reduces the energy required for spacecraft to escape. Abundant local resources, including water ice, CO2, and minerals, could produce fuel and life support consumables. Distance from Earth is significant but manageable, allowing testing of long-duration missions without completely leaving human reach. In effect, Mars can serve as a logistical, technological, and psychological proving ground for the more extreme challenges of interstellar travel. One of the critical limitations for leaving the solar system is the sheer energy cost of achieving interstellar velocities. Mars offers a solution: ICE-based fuel production. Martian resources could produce hydrogen, methane, and oxygen for rockets. Orbital refueling stations. Ships departing Mars could stockpile fuel in orbit, reducing launch mass requirements. Incremental acceleration. Using nuclear thermal or nuclear electric propulsion, spacecraft could leave Mars with higher velocities than from Earth. By transforming Mars into a fuel and logistics hub, humanity can gradually build a solar system-wide infrastructure capable of supporting longer, faster voyages. Before humans attempt interstellar travel, we must learn to sustain life independently of Earth. Habitats on Mars must demonstrate long-term stability, including air, water, and waste recycling. Energy generation must be reliable and redundant, potentially combining nuclear and solar systems. Autonomy is key. Martian crews will face delays in Earth communication, simulating the isolation of interstellar travel. Mars allows humanity to test all aspects of prolonged self-sufficient existence without committing to centuries-long missions. Robotics and AI are critical for both survival on Mars and future interstellar travel. Autonomous construction. Robots can build habitats, refineries, and launch platforms before humans arrive. Maintenance. AI monitors systems, predicts failures, and performs repairs in real time. Navigation and coordination. AI manages trajectories, adjusts orbital insertions, and calculates efficient interplanetary transfers. Experience with Mars will refine human-machine collaboration, a necessary skill for missions where crew cannot rely on Earth support. Mars serves as a training ground for human resilience. Crews must endure months of isolation, environmental risk, and limited resources. Decision-making under pressure is essential. Mistakes can be fatal. Social cohesion, leadership, and culture must be maintained over extended periods. The mental strategies developed on Mars, autonomy, problem-solving, conflict resolution, will be essential when humans venture into interstellar space, where distance renders Earth irrelevant. Mars allows practical testing of advanced propulsion systems in conditions closer to those needed for interstellar missions. Nuclear thermal propulsion, NTP, could enable faster Mars-Earth or Mars orbit transfers. Nuclear electric propulsion, NEP, provides efficient, long-duration thrust for cargo ships. Experimental fusion or antimatter systems. Small-scale tests could be conducted before committing to interstellar crewed missions. By using Mars as a launchpad, engineers can validate technologies incrementally, reducing the risks for future deep space missions. In-situ resource utilization is not just practical, it is essential for interstellar readiness. Fuel, water ice, and CO2 can be converted into methane and oxygen for rockets. Air and water. Recycling systems combined with local resources reduce dependency on Earth. Construction materials. Regolith can provide shielding, building blocks, and radiation protection. Mars becomes a testing environment for truly autonomous living, replicating the self-reliance needed in interstellar voyages. Mars allows study of hazards relevant to interstellar travel. Cosmic radiation. While Mars has a thin atmosphere and minimal magnetic protection, it provides experience in shielding, monitoring, and mitigating long-term exposure. Microgravity adaptation. Rotating habitats can simulate long-term artificial gravity. Closed-loop ecosystems. Controlled agricultural systems teach humans to maintain life support independently. Each solution refined on Mars will directly inform the design of interstellar missions, reducing unknowns and risks. If humanity is to travel to the stars, future crews must be educated in survival, autonomy, and technology. Mars provides an environment to cultivate skills under realistic conditions. Long-term missions test governance, social organization, and decision-making. Crews can develop culture and traditions that sustain human society beyond Earth. Mars is a classroom, laboratory, and community rolled into one. Essential preparation for the psychological, social, and technical demands of interstellar travel. Mars is more than a single destination. It is part of a hierarchical expansion strategy. 1. Earth, launch, development, and early infrastructure. 2. Moon, short-duration missions to practice low-gravity operations, ISRU, and remote autonomy. 3. Mars, long-duration missions with resource utilization, advanced propulsion testing, and habitat validation. 4. Outer solar system, robotic and crewed exploration to test deep space endurance. 5. Interstellar missions, built on lessons, technology, and experience gained from previous steps. Each stage builds capability incrementally, with Mars as the pivotal intermediate hub. The choice to use Mars as a launchpad has consequences beyond engineering. International cooperation may be required for funding, technology, and coordination. Ethical considerations. Who decides who goes, what risks are acceptable, and how to manage generational crews? Long-term sustainability. Mars may evolve from a research base into a true autonomous society. Distance from Earth requires foresight in politics, law, and ethics, mirroring challenges that will arise on interstellar voyages. Optimistically, 2030s, 2040s. Uncrewed and short-term crewed missions to Mars, testing ESRU and habitats. 2050s, 2060s. Sustained human presence with semi-permanent habitats and resource extraction. 2070s, 2100s. Mars-based spacecraft begin preparing for solar system departure, testing advanced propulsion, and building interstellar logistics. Mars provides a century-long platform to transform humanity from a planetary species into a system-wide civilization capable of contemplating the stars. Even with Mars as a hub, travel to stars remains decades or centuries away. Technologies like fusion propulsion, antimatter engines, or cryogenic sleep are not yet mature. Human biology and psychology impose hard limits. Mars prepares us, but it does not eliminate distance. It allows humanity to learn how to survive and operate when Earth is out of reach. Mars represents both a goal and a tool. A goal, a challenging, tangible destination beyond Earth. A tool, a laboratory for life support, autonomy, propulsion, and human society in isolation. As a launchpad, Mars enables humanity to build the infrastructure, technology, and experience needed to consider interstellar travel. It transforms distant ambition into actionable preparation. This section closes by asserting that the journey to the stars will not begin with a single leap, but with measured, disciplined, and incremental steps, Mars being the first and most critical of those steps. The next section will examine how human, robotic, and technological collaboration beyond Mars can extend our reach even farther, bridging the gap from solar system colonization to the threshold of interstellar exploration. By the time humanity establishes a foothold on Mars, we will have learned a critical truth. Survival and exploration beyond Earth are not achieved by humans alone. Robots, artificial intelligence, and automated systems will be indispensable partners in every phase of space exploration, particularly when the goal is to extend human reach to interstellar distances. This examines how human-robot collaboration can expand our capabilities, reduce risk, and serve as the bridge between the solar system and the stars. Even with Mars as a launch pad, human beings are constrained by biology, lifespans, radiation tolerance, and microgravity effects limit duration in space. Psychology, isolation, stress, and decision-making under prolonged uncertainty create risks for crew cohesion. Resources, every kilogram of food, water, and fuel carries exponential cost in energy and logistics. No matter how advanced, humans alone cannot conquer interstellar distances or manage the vast infrastructure required. Machines are not just tools, they are multipliers of human capability. The journey beyond Mars begins with robots. Reconnaissance, mapping terrain, scanning for hazards, and identifying resources on asteroids, moons, and planetary surfaces. Construction, autonomous assembly of habitats, refineries, and launch platforms before humans arrive. Maintenance, monitoring and repairing life support systems, energy infrastructure, and propulsion units. Robots act as extensions of human presence, performing tasks that would be dangerous, impossible, or inefficient for humans in situ. Artificial intelligence can complement human cognition in several ways. Predictive maintenance. AI can detect system failures before they become catastrophic. Autonomous navigation. AI manages complex orbital maneuvers, interplanetary trajectories, and launch sequences with minimal human oversight. Resource optimization. AI can calculate efficient use of fuel, water, and energy, especially in environments where resupply is impossible. As distance from Earth increases, AI moves from assistant to co-pilot, advisor, and sometimes leader, capable of operating autonomously when communication delays make human intervention impossible. Mars provides an ideal environment to test collaborative human-machine workflows. Construction. Humans direct robots to build habitats, mining operations, and fuel plants. Exploration. Crews ride rovers remotely operated by AI or collaborate with drones in hazardous environments. Maintenance and repair. Human ingenuity handles unexpected failures, while AI handles routine monitoring and predictive tasks. These lessons are critical for interstellar travel, where humans cannot supervise every system in real time and must rely on autonomous partners. Before humans venture between stars, machines will explore, mapping, scouting nearby star systems, identifying planets, hazards, and potential resources. Experimentation, testing propulsion methods, radiation shielding, and life support analogues on long-duration robotic missions. Communication, serving as beacons and relays for eventual human missions. Distance dictates that robots travel first, expanding knowledge and reducing risk for future crewed missions. A realistic interstellar mission requires a tightly integrated system of humans and machines. 1. Crewed habitat, where humans live, sleep, and work. 2. Autonomous cargo modules, carry resources, perform construction, and monitor environmental conditions. 3. AI overseers, coordinate all modules, manage contingencies, and optimize energy usage. 4. Remote scientific units, deployed ahead of the crew to gather data on interstellar space, radiation, and potential hazards. The interplay between these components maximizes efficiency, minimizes risk, and compensates for human vulnerability. Humans cannot carry everything required for decades or centuries of interstellar travel. Robotic partners extend resource efficiency, mining asteroids or moons for water, metals, and other materials. Recycling and refining onboard supplies with AI assistance. Constructing shields, spare parts, and infrastructure autonomously. Without robotic augmentation, resource limitations make long-term missions infeasible. Distance amplifies scarcity. Automation mitigates it. Humans traveling beyond Mars face increasing exposure to cosmic rays and solar particles. Machines serve as both shields and first responders. Shielding structures. Robots assemble protective barriers from local materials. Monitoring systems. AI tracks radiation doses and alerts crew to high-risk events. Emergency protocols. Autonomous systems can initiate protective measures faster than humans could react. The collaboration between humans and machines preserves life where isolation makes intervention impossible. Mars is a natural laboratory for autonomous operations. Crews must rely on robots for daily survival tasks. AI systems manage critical life support and energy functions. Communication delays simulate interstellar distances, forcing humans to operate independently while collaborating with intelligent machines. Experience gained on Mars teaches how to trust, integrate, and optimize human-machine teams for interstellar missions. For missions lasting multiple decades or centuries, robots may continue operating as humans age or perish. AI can maintain knowledge continuity, ensuring that the mission remains coherent across generations. Human decisions focus on creativity, problem-solving, and ethical governance, while machines handle repetitive, dangerous, or precision-critical tasks. Interstellar survival depends on delegating the right tasks to the right partners over extended time. Distance beyond Mars introduces delays of minutes to hours, making real-time guidance impossible. For interstellar missions, these delays grow to years. Machines must operate independently, capable of responding to hazards without human input. Humans must trust AI to manage life-critical systems. Data collected en route may not be interpretable by Earth until decades later. Human-machine collaboration ensures functionality when Earth is irrelevant in real time. The lessons learned on Mars can scale. Small robotic systems assist small crews. Larger fleets of autonomous machines can support larger colonies or multi-generational ships. AI coordination allows distributed systems to function as coherent networks, managing resources, navigation, and exploration. Scaling is essential for any mission beyond the solar system, where single points of failure are unacceptable. Delegating authority to machines raises ethical questions. How much autonomy should AI have in life or death decisions? Who programs mission priorities when humans cannot intervene for decades? How do humans ensure that robots act in accordance with human values over long time scales? Mars serves as a testing ground for these dilemmas, allowing society to establish governance protocols before committing to interstellar missions. This section emphasizes that humans and machines are not competitors, but partners in space exploration. Mars provides the proving ground for autonomous operations, human-machine trust and workflow, resource management, radiation mitigation, and life support, social and ethical frameworks for extended isolation. Interstellar travel cannot be achieved by humans alone. The combination of human ingenuity and machine endurance creates a sustainable path for ventures beyond the solar system. In the next section, we will explore the role of energy, propulsion, and physics in transcending the limitations of the solar system, bridging the lessons from Mars and human-machine collaboration to the technical realities of interstellar travel. After mastering survival, autonomy, and human-machine collaboration on Mars, the next frontier is propulsion and physics. This section explores the fundamental challenges and theoretical solutions necessary to move beyond the solar system. It asks, how can humans, or even robotic emissaries, traverse the vast distances separating stars within a practical time frame? Even with Mars as a launch pad, the distances involved are staggering. Proxima Centauri, 4.24 light-years away. Alpha Centauri system, 4.37 light-years. Barnard's star, 6 light-years. One using conventional chemical rockets, reaching Proxima Centauri would take tens of thousands of years. Energy and mass requirements make crewed travel infeasible. The laws of physics dictate these constraints. Overcoming them requires fundamentally new approaches to propulsion. Chemical rockets, while effective within the solar system, are limited by energy density. Chemical fuel releases only a small fraction of the energy stored in matter. Exhaust velocity limits acceleration and maximum achievable speed. Fuel mass scaling. Increasing speed requires exponentially more fuel. Even nuclear thermal propulsion, NTP, or nuclear electric propulsion, NEP, can only shorten interplanetary trips, not make interstellar travel practical. Nuclear propulsion harnesses the energy of atomic nuclei, nuclear thermal rockets, NTR. Heat hydrogen with nuclear reactions to achieve higher exhaust velocity than chemical rockets. Nuclear electric propulsion, NEP, converts nuclear energy to electricity to power ion engines capable of continuous thrust over months or years. Advantages: increased efficiency and higher velocities, feasible for cargo missions and long-duration Mars travel. Limitations: complex engineering and radiation shielding requirements. Insufficient speed to reduce interstellar travel to human lifespans. Fusion propulsion uses reactions similar to those powering the Sun. Fusing hydrogen isotopes releases tremendous energy. Exhaust velocities can reach a significant fraction of light speed. Continuous thrust allows acceleration over months or years, gradually building speed. Potential applications: cargo ships carrying supplies for interstellar missions. Crew modules benefiting from higher velocity to reduce travel time. Challenges: achieving controlled fusion on Earth remains difficult. Compact, reliable fusion reactors for spacecraft have not yet been realized. Fusion represents a promising near-future pathway to interstellar travel. Antimatter annihilation releases energy orders of magnitude greater than fusion or fission. 1 gram of antimatter yields as much energy as thousands of tons of chemical fuel. Propulsion systems using antimatter could approach a significant fraction of light speed. Practical obstacles: production, extremely limited and expensive. Storage. Containing antimatter safely is a major engineering challenge. Safety. Any containment failure is catastrophic. Antimatter propulsion remains theoretical, but it represents the ultimate energy solution for rapid interstellar travel. Light sails use radiation pressure to propel spacecraft. Thin, reflective sails are pushed by sunlight or powerful lasers. Acceleration is slow but continuous, with minimal onboard fuel requirements. Applications: small robotic probes to nearby stars. Potential for near light-speed travel in miniature payloads. Limitations: scaling to crewed missions is difficult due to mass constraints. Requires massive laser infrastructure to achieve high acceleration. Light sails demonstrate that creative physics-based solutions can circumvent fuel limitations. Speculative physics offers radical possibilities. Warp drives. Theoretical manipulation of spacetime could allow effective faster-than-light travel without violating relativity locally. Wormholes. Hypothetical shortcuts connecting distant points in spacetime. Challenges, entirely unproven experimentally. May require negative energy or exotic matter not yet understood, likely centuries or millennia away from practical application. While highly speculative, these concepts expand the realm of possibility and inspire research into extreme propulsion methods. Near light-speed travel introduces relativistic effects. Time passes slower for travelers than for observers on Earth. A journey to Proxima Centauri at 90% light speed could take them 4.7 years for the crew, but decades on Earth. Implications: interstellar voyages could be feasible within human lifespans, despite distances. Crews experience reduced time, but Earth-based communication and societal continuity are disrupted. Time dilation is both a limitation and a tool, allowing travelers to compress subjective travel time while distance remains vast. At high velocities, even microscopic interstellar particles become deadly projectiles. Protective shielding is critical. Magnetic or plasma-based shields may deflect charged particles. Long-duration exposure to cosmic rays requires careful habitat and shielding design. Distance magnifies these hazards. Effective propulsion alone is insufficient without integrated protection. Traveling at significant fractions of light speed demands extraordinary energy. Continuous acceleration requires sustained power sources. Every additional kilogram of payload exponentially increases energy requirements. ISRU, local energy generation, or pre-positioned fuel, may reduce initial mass constraints. Interstellar travel is not just about propulsion. It is a resource management problem on a cosmic scale. Using Mars as a launch pad enables testing of propulsion. 1. Mars orbit testbeds. Test NTP or NEP in deep space conditions. 2. Long-duration robotic missions. Assess propulsion efficiency and reliability. 3. Crewed Mars expeditions. Validate life support, radiation shielding, and autonomous operation. 4. Interstellar robotic scouts. Deploy light sail or fusion-powered probes to nearest stars. Each step reduces unknowns and refines technology before committing human crews. A feasible interstellar mission would likely combine multiple technologies: primary propulsion, fusion or antimatter engines for crewed modules, auxiliary propulsion, light sails or ion engines for cargo modules, autonomous systems, AI-guided probes and support vehicles, shielding, magnetic and material defenses against cosmic radiation and interstellar debris. Integration of these components is essential for survival, speed, and mission success. Conventional rockets are insufficient. Fusion and antimatter propulsion offer near-term and ultimate solutions. Light sails provide a fuel-less alternative for robotic missions. Relativistic effects, radiation, and resource constraints define practical limits. Mars serves as a proving ground, autonomous AI as a collaborator, and physics as both obstacle and guide. Together, these elements prepare humanity for the leap from planetary habitation to interstellar ambition, demonstrating that while distance is vast, it is not insurmountable with ingenuity, preparation, and perseverance. The final section will synthesize the lessons from all previous sections, examining how humanity's current capabilities, Mars-based preparation, technology, and collaboration might realistically enable travel beyond the solar system. After traversing the journey from Earth to Mars, examining the tyranny of distance, exploring technologies, human-machine collaboration, and the physical barriers to interstellar travel, we arrive at the culmination of humanity's understanding and preparation for venturing beyond the solar system. Section 14 synthesizes lessons from all previous sections to envision what practical, long-term human interstellar exploration might look like, what steps are required, and how we can reconcile ambition with reality. Humanity's present capabilities are constrained yet impressive. Earth orbit operations. The International Space Station demonstrates long-duration human survival and closed-loop life support for months to years. Moon and near-Earth missions. Humans have proven the ability to reach, land, and return safely. Mars readiness. Robotic explorers have mapped terrain, discovered resources, and validated scientific interest. Propulsion. Chemical rockets are sufficient for intrasolar system travel, while nuclear propulsion is on the near horizon for faster transit. These accomplishments form the foundation on which interstellar ambitions must be built. Mars is the critical proving ground. Life support systems, closed-loop habitats, recycling, and ISRU provide experience for long-duration space living. Autonomy. Crews must operate independently, a necessary skill for interstellar missions where Earth guidance is delayed by years. Human-machine collaboration. Robots and AI serve as essential partners for resource extraction, maintenance, and hazard mitigation. Psychological resilience. Social cohesion, governance, and long-term mental health are tested in an isolated environment. Mars is not just a destination, it is a learning environment for the complexities of interstellar survival. To move beyond the solar system, humanity must integrate multiple advanced technologies. 1. Propulsion, fusion, antimatter, or light sail systems to achieve significant fractions of light speed. 2. Energy generation. Onboard nuclear reactors or harnessed resources for sustained power. 3. Life support. Advanced closed-loop systems capable of supporting multiple generations or long-duration crewed missions. 5. Radiation shielding. Magnetic fields, material shielding, or innovative plasma barriers to protect against cosmic radiation. 6. Automation and AI. Systems capable of independent decision-making and maintenance when humans are unavailable or incapacitated. The synthesis of these technologies is essential. No single breakthrough will suffice. Interstellar travel demands convergence of engineering, physics, biology, and AI. Even with advanced technology, humans remain a limiting factor. Lifespan. Travel at near-light speed may use time dilation, but crew health, reproduction, and aging are constraints. Psychology. Isolation, confinement, and the knowledge of leaving Earth indefinitely present mental challenges. Social systems, governance, ethics, and decision-making must persist across long-duration missions or generational crews. Human resilience must match technological capability. The most sophisticated spacecraft cannot compensate for poor crew management, low morale, or social breakdown. Given the distances involved, generational ships may be necessary. Crews live, age, reproduce, and die during transit, passing the mission to their descendants. Life support and habitat systems must function for centuries, with redundancy and repair capacity. Culture, education, and societal norms must be maintained to ensure purpose and cohesion. Generational missions are not just engineering problems, they are social and ethical experiments in long-term human survival. To shorten mission duration from a human perspective, cryogenic systems could slow metabolism, allowing a single crew to survive decades or centuries in stasis. Challenges include avoiding cellular damage, managing long-term organ function, and ensuring safe revival. Partial or rotational cryosleep could reduce resource consumption and mitigate psychological strain. While currently speculative, suspended animation is a potential multiplier for interstellar feasibility. A realistic interstellar mission might consist of several integrated elements. 1. Crew modules, habitats designed for life, work, and recreation, with redundancy in every system. 2. Cargo modules, carrying fuel, resources, and spare parts, potentially autonomous. 3. Robotic scouts, preceding or accompanying the crew to assess hazards and provide continuous feedback. 4. Propulsion modules, fusion or antimatter engines capable of sustained thrust. 5. Shielding systems, protecting both crew and critical machinery from radiation and micrometeoroid impacts. AI command systems, monitoring all systems, managing contingencies, and coordinating human-machine operations. The mission becomes a network of interdependent components, not a single vehicle, reflecting the complexity of interstellar travel. Distance magnifies scarcity. Food, water, oxygen, and energy must be recycled or produced on board. In situ resource utilization may be possible if intermediate waypoints, asteroids, moons, Mars are used. AI and robotics reduce human consumption by performing labor-intensive and high-risk tasks. Interstellar missions require holistic resource management, integrating physical, biological, and technological systems into a sustainable whole. Traveling at high speeds exposes humans to unique hazards, cosmic rays, and interstellar radiation. Continuous exposure increases cancer risk and accelerates aging. High-velocity collisions with dust or particles. Even tiny objects can cause catastrophic damage. Solar and stellar flares require shielding and monitoring systems. Engineering solutions, magnetic shields, water barriers, material armor must complement human vigilance and AI management. Distance imposes profound effects. Communication with Earth becomes delayed by years or decades. Mission planning must account for relativistic time dilation, where the crew ages slower than Earth observers. Decision-making autonomy is essential. The crew and AI must function independently for long periods. Time itself becomes both ally and constraint, influencing mission design and crew experience. Interstellar missions raise unprecedented ethical questions. Generational consent. Descendants may inherit missions they did not choose. Risk versus reward. Exposure to danger must be balanced against scientific and societal benefits. AI authority. Decisions delegated to autonomous systems require ethical frameworks. These challenges are magnified by distance and isolation, making Mars and near-Earth experiments critical for developing ethical governance structures. Practical interstellar travel requires a phased strategy. 1. Earth-based research, propulsion, AI, cryogenics, and habitat technologies. 2. Lunar and Mars operations, test autonomy, life support, and human resilience. 3. Solar system exploration, robotic and crewed missions to outer planets. 4. Interstellar robotic scouts, assess nearby stars and planets. 5. Crewed interstellar missions, utilizing validated technologies, AI systems, and Mars-based infrastructure. Stepwise progression reduces risk and ensures that every milestone builds the foundation for the next. No single nation or discipline can achieve interstellar travel. Engineering, physics, biology, and AI must converge. Nations must cooperate to pool resources, knowledge, and expertise. Cultural, political, and ethical frameworks must be developed collectively. Humanity's survival beyond the solar system requires coordinated global effort. Synthesizing lessons from all prior sections, the vision emerges. Mars teaches survival, autonomy, and resourcefulness. Robotics and AI extend human capability, managing risk and labor. Advanced propulsion and energy systems confront the tyranny of distance. Life support, governance, and ethics prepare humans psychologically and socially. The stars are distant but not unreachable. Humanity's path requires preparation, patience, and incremental mastery of both technology and human adaptability. Humanity stands at the threshold. Technologically, we are approaching Mars-based readiness. Socially and psychologically, we are learning autonomy and resilience. The physical laws of propulsion and energy define clear barriers, but they are not insurmountable. Distance remains vast, time remains long, and hazards remain lethal. Yet, by combining Mars-based preparation, technological advancement, human-machine collaboration, and ethical foresight, humanity can move from dreaming of the stars to taking the first cautious steps beyond the solar system. The future is not guaranteed, but the path is clear. Incremental mastery of survival, technology, and autonomy will allow humanity to traverse the vast cosmic ocean, one deliberate step at a time. Humanity may not yet reach the stars tomorrow, but the seeds of interstellar exploration have already been planted. Mars is the nursery, AI and robotics are our guides, and physics is both challenge and roadmap. The journey from the cradle of Earth to the stars is long, but it is within the realm of human aspiration and ingenuity.